Okay, let's dive right in. When most of us picture a human skeleton, we tend to imagine something static, right? Like a rigid, dry frame that basically just acts as a coat hanger for our muscles and organs. Well, today we are going to completely challenge that idea. In this explainer, we're exploring the true architecture of osteogenesis and bone remodeling. We're going to look at the skeleton not as a fixed structure, but as a dynamic, living construction site, one that is literally tearing itself down and rebuilding itself from the ground up every single day of your life.
So, here is our roadmap for today. First, we'll cover before birth and bone foundations. Second, childhood and the mechanics of growth. Third, adulthood and the construction site. Fourth, the molecular managers pulling the strings behind the scenes. And finally, we'll map out the lifelong timeline of our bone mass.
All right, section 1, before birth, bone foundations. Because long before we ever take our first breath, our internal blueprints are already hard at work, laying the groundwork. The very first step of bone formation relies on something called mesenchymal cells. Think of these as the incredibly versatile, foundational building blocks of embryonic connective tissue. Right around 8 weeks of gestation, these mesenchymal cells group together to form what is essentially a soft cartilage template, often called the cartilage anlagen. From there, it's pretty cool, specialized cells called chondroblasts move in and actually begin hollowing out a central medullary canal, which establishes a primary ossification center right in the middle of this soft cartilage model.
Now, what's really fascinating here is the stark contrast between the two completely different ways our body lays down its skeletal foundation. What we just described, starting with a cartilage template that eventually turns into bone, is called endochondral ossification. And that's the process used to build our long bones, like the ones in our arms and legs. But your body has a completely different strategy for flat bones, like your skull. The second method is called intramembranous ossification. Here, the body just skips the cartilage phase entirely. Those foundational mesenchymal cells differentiate directly into bone-building cells, known as osteoblasts. It's an incredibly efficient way to rapidly build the protective plates of the skull.
Moving on to section 2, childhood, the mechanics of growth. With the foundation set, let's look at how those centers actually start expanding. So during childhood, the action really shifts to the ends of our long bones, specifically to secondary ossification centers and the growth plates, which clinicians call physes. Inside these growth plates, a highly choreographed 4-step dance is happening with cells called chondrocytes. Step 1 is proliferation. The chondrocytes multiply rapidly. Step 2, hypertrophy. They literally swell up and grow in size. Now, step 3 is wild. It's apoptosis. These cells intentionally die off, dramatically sacrificing themselves just to make room. And finally, step 4. Capillaries invade the space left behind, and that calcified cartilage is replaced by a mineralized matrix. This fresh trabecular bone is literally how longitudinal growth happens. I mean, it's exactly how we get taller.
But again, our flat bones do things a bit differently. Because they were formed without that initial cartilage template, they expand outward through a process called appositional growth. Instead of growing from a plate at the end of the bone, they expand by surface deposition. Just picture a bricklayer walking around the perimeter of a building, constantly adding a new layer of bricks to the outside wall to make the whole building wider and thicker. That is appositional growth in action.
Which brings us to section 3, adulthood, the construction site. Once we stop growing taller, the whole narrative shifts from bulk expansion to daily microscopic maintenance. Welcome to the highly active construction site inside you right this very second. The star of the show here is the BMU, or the Bone Multicellular Unit. You can think of the BMU as a highly localized, specialized cellular crew. You see, to keep our bones strong and repair all those tiny microfractures from everyday life, we need a demolition crew to clear out the old, weakened material and a rather overworked builder crew to pour fresh concrete. The life cycle of this BMU crew happens in 4 sequential phases. First up is resorption. The demolition cells, which are called osteoclasts, attach themselves to the bone surface and actively secrete acid to literally melt away and demolish the old bone. Second is the reversal phase, where the site is completely prepped and cleaned up. Step 3 is the recruitment of the builders, our osteoblasts. And finally, step 4, these osteoblasts get straight to work depositing brand new bone matrix to fill in the excavated area. It's just a seamless, ongoing cycle of microscopic destruction and creation.
Section 4, the molecular managers, regulating the crews. So we know what the cells do, but how do they know when to do it? Let's zoom into the cellular communication level. The absolutely crucial point here is this very specific signaling loop, RINC, RINC-L, and OPG. Think of this as the secure communication system for your bones demolition crew.
The demolition cells, those osteoclast precursors, have a receptor called rank. When another molecule called rank L binds to it, it acts as a massive signal, telling the demolition crew to survive, multiply, and start tearing down bone. But obviously, we don't want too much bone destroyed, right? So the body produces OPG. OPG acts as a clever decoy receptor. It grabs onto rank L before it can ever reach the demolition crew, effectively blocking the signal and putting the brakes on bone breakdown.
And this brilliantly illustrates how the body balances building and resting on the formation side, too. On one hand, we have want signaling. When want activates beta-catenin in the osteoblasts, it acts as a massive green light for the builders, promoting bone formation and even producing that decoy OPG to stop the demolition crew. On the other hand, we have sclerostin. This is secreted by osteocytes, and its entire job is to inhibit want signaling. So sclerostin acts as the brakes, reducing bone formation so the builders don't go into overdrive. It is a stunning, delicate balance that your body manages every single second of the day.
Zooming out slightly from those localized cells, we've got an absolute alphabet soup of systemic regulators that tip the balance either toward building or demolishing. Looking at the promoters of formation, our bodies heavily rely on things like estrogen, testosterone, vitamin D, and bone morphogenetic proteins, or BMPs. Growth and thyroid hormones also play a huge role here in maintaining chondrocyte stages during our growing years. Conversely, to unleash the demolition crews via resorption, the body utilizes parathyroid hormone, interleukin-1, and glucocorticoids.
Finally, let's move to Section 5, the lifelong bone timeline, mass across life. We need to see how these microscopic crews shape the trajectory of our entire lifespan.
When we connect everything we've just discussed into a macro timeline, we see how the race to peak density plays out. In childhood, the balance is heavily skewed towards the builders. We get rapid growth, proliferation, and bone formation. This massive construction project continues full steam ahead until early adulthood, which is where we hit our peak bone mass. This is literally the highest bone density you will ever have in your life. But as we enter our fourth decade, our 30s, the balance shifts. The demolition crews slowly start outpacing the builders, leading to a gradual, inevitable decline in bone density for the rest of our lives.
Which brings us to the final provocative thought I want to leave you with today. We've seen that the skeleton isn't just some static coat hanger. It's an incredibly active, living construction site, constantly balancing between demolition and rebuilding based on systemic hormones, mechanical stress, and intricate cellular signals. So looking at your own daily habits, your nutrition, your physical activity, how is your current lifestyle influencing those microscopic construction crews inside your skeleton right now? Are you giving your builders the signals they need to keep pouring fresh concrete? Think about it. Thanks for exploring the dynamic world of osteogenesis and remodeling with me today, and I'll catch you in the next explainer.